Our next speaker is Mihailo Isakov. He's a founder and CEO of Bulsi, and he's working with high-performance computing, machine learning, and computer architecture. Mihailo, you don't have a microphone?
Not yet.
Not yet. Please go there, and I'll continue. In his talk, I'm so sorry. Just a second. In his talk, you will need custom chips soon, where high performance and energy efficient computing is going. Mihailo will tackle the pivotal question: where does computing go when we reach the limits of single-threaded performance? Join us as he addresses the concerns of those navigating latency-sensitive and energy-bound computing challenges. With a deep understanding of real-time learning and interference inside CPU, microarchitectures showcased in his PhD defense, Mihailo is leading Bulsi, a groundbreaking generative hardware startup. His vision is to transform any code base into functional circuits without the need for in-house hardware experts, right?
Thank you.
Okay, the floor is yours.
Thank you. All right, so today we'll be talking about how do we fix some hard computational problems for which there is no simple answer, like throw more cloud at it. Just as a brief introduction, moved a lot across grad school. My advisor was kind of a hotshot, so we moved from Oregon to Massachusetts, Texas, Arizona, Illinois. After that, I started a chip design startup where we were trying to basically make it accessible for software engineers to build and deploy hardware in like an order of magnitude faster. Here's who this talk is aimed at. This will be interesting to you if you have some maybe latency-bound problems, or if you're spending a lot on cloud compute, or if for your specific problem you can't just go to AMD or Intel and buy a better CPU. But let's give credit where it's due. Basically, we are in a very lucky spot. Startups can compete with big companies. Salaries are good. We do owe this to advances in chip manufacturing. There's not a lot of other industries where we see this sort of exponential growth, right? Your car does not get twice as more fuel efficient every 2 years, nor does it get twice as fast. We have that, and software engineers find a way to ruin that, but it's fine. We would like to keep this up, and we are struggling. We're in a pretty tough spot because we're hitting the limits of physics. So I would like to look at some history. Moore's law, alive and well. We are pushing more transistors, maybe not as dense, but in larger chips. This slide from 99, I think from Intel, was interesting because it showed that, hey, one of the main reasons how we push more compute is just push more power. And this used to scale, and people were joking, well, 10 more years, and you basically have a nuclear power plant in your desktop. We're not far off of that. But what did happen is that our power usage kind of capped off around 2005, not because of lack of cooling. It's not that we can't cool them enough. There was a thing called Dinard scaling. Basically, I doubled the amount of transistors I put in a certain piece of area, let's say a centimeter square. And if they use the same amount of power, I double the amount of power I use. But Dinard scaling said, yes, there's twice as many of them, but they're twice as efficient. So you can just keep putting more logic in the same area, and you use the same amount of power per area. That stopped working at some point. We used to be able to run all of the cores on all the time, but no longer. After around 2006, power per area no longer is constant. And this is typically called the dark silicon problem. You need to keep a large portion of your chip off, maybe different parts at different times, but you need to keep it off for cooling reasons. So yeah, you could say, okay, I can't push more power, but I can probably clock it or something to get more single-threaded performance. Overclockers do it all the time. Sure, but we stopped doing that as well because your power usage typically grows quadratically with frequency. Double the frequency, quadruple the power. So that's bad. So Okay, what do we do now? Well, okay, we can just throw our heads at it and build better CPUs, deeper pipelines, wider number of instructions issued per cycle. There's a lot of tricks we can do here, like branch prediction, out-of-order execution, hyperscalers, so on and so on. But there's a limit to this, and we are hitting those limits. Other than maybe like Apple's some of the recent advances, we are pretty much as close as we can get without some pretty big information theory breakthroughs. So what we are seeing is that single-threaded performance has also tapered off, right? We are seeing an exponential increase, but the slope is not as good as it used to be. So that's ugly. And do note that this is normalized for frequency, so these are actually architectural gains. So we get a lot of transistors. We don't know what to do with them, so we do the simple thing, which is throw more cores in. And this has been happening for almost 10 years now. We are in the hundreds. But this works if you have strong scaling for a problem. That's often not the case, right? Not all problems are parallelizable. You have Amdahl's law that stops you from utilizing all those cores for your problem. So this does not really fix everyone. At the same time, the costs of building multi-cores are huge. You need to think about stuff like cache coherency. You see Apple literally trying to avoid building NUMA cores where different cores have different speeds to memory and so on. It gets very, very complicated. So some insight is we gave people 8 years of exponential progress, right? And right now, energy efficiency is the name of the game. If I give you cheaper compute, you can do more with it, so you get more compute out. And energy and cooling are a majority of data center lifetime cost. I work a lot with supercomputers. They're something like 70% of the lifetime cost of a supercomputer, just energy and cooling. Staffing is 3% for a lot of US data supercomputers. Hardware is maybe 10. So we have a lot of transistors. We can't turn them all on. So what can we do? Two approaches. One would be adaptive computing. The idea there is have architectures reconfigured for your workload at runtime and maintain basically the view that programmers keep of the CPU. It's general, but it's not as efficient as it could be if you built custom purpose accelerators for a problem. So that would be like, GPUs or TPUs nowadays, or cryptography. You already have that in your laptops or phones. Or codecs, the thing that lets you watch 10 hours of Netflix on a battery. But these need to happen in design time, and they're good for typically one thing. So just to illustrate the first part, the adaptive computing, we are running some workloads. We build CPUs for a variety of workloads. We don't really know what the workloads of tomorrow are. It can be everything from serving the web to doing databases or graphs. And these are very different types of tasks. And they have different requirements. You want a different architecture for each one of these, right? But you don't have good insight unless you're Apple, I guess. Intel does not know what exactly their customers are executing. It's really hard to get access to all of those binaries. So you kind of have a very poor map of the domain. And the landscape is changing. Basically, you get surprised. LLMs come in, the workloads that you want to be running are completely different than 2 years ago. So, additionally, you don't really know user goals. These change often, for example, because of security issues. So what can we do? Well, we build these architectures to be one size fits all. Basically, cram all the bells and whistles in one spot and sell it. And you don't need, branch prediction if you're doing databases, but you still turn it on. You might not need caching if you're doing streaming applications, but you still have it on. It actually uses about 50% of your power. And unless you go into BIOS, you might not be able to turn it off. So we kind of optimize to have something that is kind of okay at everything. And again, design with stale data. And it's static, doesn't change over time. So what can we do? Well, the idea with adaptive architectures is have a CPU that figures out, oh, here's the task I'm running, and only, for example, turn on the components it actually needs to execute that. And quite often, it's 10% of your CPU. And when your workload changes, you adapt, and you adapt, and you adapt, and you adapt. So you're carrying all those bells and whistles, but you're not using them. So you're only satisfying the currently running workloads. And the interesting part is there's a lot in your CPU that you as a software engineer don't have access to. What's my cache hit rate? What's my branch prediction rate? How is my network on chip doing? I typically, without some hardware support, don't have access to this, and I don't use it to write better software or more efficient software. Also, it changes on a microsecond level. You probably won't be able to benefit from it, but hardware can. So the idea is, let's say I have a large multi-core, and each node, each processor might have some compute. It has some local caching. It has a network on chip router. What we want to add is a sort of an introspection layer where it has sensors into all of this local architecture, and it has some actuators. Oh, turn off half of the reorder buffer, turn off half of the cache, change the branch prediction algorithm, change the eviction policy, and so on. All of these decisions are microsecond level decisions, often nanosecond level, to make full use of the benefits. So you can think of them as basically JITs for hardware. They're kind of changing not your software, but your hardware at runtime. So yeah. But they need really fast decision making. And just to kind of validate this, I spent a lot of time analyzing supercomputers, specifically Argonne National Labs Theta and Lawrence Berkeley's Cori. HPC systems are very complex beasts, much more complex than a CPU or a data center, because they have typically bespoke networking, bespoke storage systems, a lot of caching layers, and so on. And they're multi-tenant. All of these workloads kind of interact, not in a good way. And I focus mostly on diagnosing our bottlenecks, not because I want to be doing that, but because that's the only thing visible from software, and we need to start somewhere. I/O is interesting in HPC because it can debilitate you. It can give you a 100x slowdown compared to what the system can do if you make 1 out of the 1,000 possible small mistakes. Using these systems is just hard, and it takes a lot of expertise. But that's good. We get high-level insight into it. We get to view the large system and pretend it's a small system. So we look at some 8 million jobs, and I won't bore you too much with the details, but we build models to predict how jobs will perform on supercomputers. And we find that everything that we know from the software and from hardware performance counters and so on accounts for about 50–60% of the variance between supercomputing jobs, variance in runtime. They still oscillate 10% up or down in performance due to things that you simply cannot measure. These are cache misses that you cannot account for because of workload interactions. These are drop packets and so on. So there's a lot of microarchitectural noise that you cannot see from software. Hardware has to come in, either provide support or actually act on that data immediately to get that 10%. But as we show later, it's not 10%, it's a lot more. There's a lot of space to make energy savings that you can later trade into performance, so throughput or latency savings. So adaptive CPUs long-term might give us 10 more years of this exponential growth, probably not more than that. You might not want to use them, go that way and go for accelerators instead, because there's a lot of really interesting new technologies that we can use, lots of new primitives. Processing in memory is amazing for accelerating neural networks, or you might want to use phase change memory, which gives you, you can store stuff after power off, but it's considerably faster. Or use analog computing, or use stochastic computing, or asynchronous ones that can have orders of magnitude lower power. So custom chips can improve your throughput, energy efficiency, latency, often 1000x if you're building a big one. If you have a workload that demands it and you're willing to pay, they're your solution long term. And you already use a lot of them, right? Video codecs, as I mentioned, our we all have GPUs nowadays. Cryptographic hardware so that you can have always-on encryption of your hard drive and so on without affecting your throughput. And when you look at the modern CPU, like I think this is the A14, you see that in the bottom left, in the left part, there's 4 performance cores. And then you look at the beast of a GPU and the relatively large neural engine, and you realize that, wow, it's about twice the size of the CPUs. So we're taking all of these transistors and throwing them on stuff that is not necessarily used all the time. You don't use a neural engine that often. You use a CPU constantly, but they got awarded the same amount of space, which is interesting. So again, kind of working around the power issues and throwing transistors at various smaller and smaller problems. But this is, again, not a perfect solution. It takes a lot of money to develop a chip. In modern nodes, like 3 nanometers, it takes about $1 billion, I think someone reported about NVIDIA recently. And hardware engineers are in a really tough spot. On one end, you can't ship a fix to a bug. So if you ship bad silicon, you're in a pickle. On the other end, your competition is exponentially improving. So if you delay a launch by a year, they might just outrun you, like happened to, I think, Voodoo Graphics back in '95. However, miniaturization is stopping. What happens then? What happens when we hit 0.5 nanometer and we can't go smaller? Well, we're not going to stop pushing R&D money anywhere. We're just going to push it somewhere else. So optimize for yield, make sure that all of the chips on a wafer work, or make it just cheaper to build a design. Basically what we see with Skywater fabs. Or have better time to market. Or build chiplets and so on. So the bet that we have is that manufacturing costs will plummet a lot. We need to make chip design costs plummet as well. And what we are trying to do is allow software engineers to take a legacy code base and find a hotspot quickly and deploy the 50 lines of code that is 90% of the compute for them, deploy them to a custom chip or just an FPGA. So chip design and validation are the bottleneck here. We have hardware like FPGAs from Xilinx and Altera, got acquired by AMD, got acquired by Intel. Amazing machines, really, really hard to use them. Why? Well, hardware design is not programming. You're not writing a single-threaded program. You're writing basically a distributed system, except that you don't have 8 cores. Now you have a million circuits that are talking to each other. They're heterogeneous. They have very specific timing requirements. So you have to have your components work correctly and work in sync. The in sync part is the problem. We don't have a type system for your timing, which kind of led to the fact that there are no package managers. I can download code off GitHub, but it's relatively hard to understand what kind of interface, what kind of handshake this 5-phone wants, and to use it correctly. And again, time to market is at odds with verification. So what we believe we need is sort of a software to hardware compiler that handles the timing for you, but not in the high-level synthesis sense. There has been a lot of attempts at doing this, and they typically all pick a language and make sure that that language can get compiled into circuits. BlueSpec did it with Haskell, multiple approaches in industry with C++, a lot with Python, but they typically make you write software as if you're a hardware person. You can't use all the benefits of a language. Oh, you can't use a recursion. Oh, you can't use polymorphism. Or you can't use a ton of these interesting tools in a language that make me want to use that language, right? So we have a way around that. The real goal here is I want to be able to just run it on legacy software and get it to run. Basically, just give me MongoDB or something and ask it to optimize the query engine. And finally, scale with compute, not with headcount. Just don't require the user to keep optimizing the code to fit the better hardware. So my ask is basically, if you have a tough computational problem, if you're spending a lot of money on it, or if you're actually like latency bound as in high frequency trading or something, I would love to talk to you. Thank you. Any questions?
Do we have questions? Okay. Please, microphone. Can we?
Or you can tell it to me and I'll repeat it.
Just a second. Yes, we have
Just for
time.
everyone here.
We have time.
I have a question, AMD or Intel, and why?
Whatever is currently giving you the best bang for the buck, which is right now AMD with Vcache. Any other questions?
One more?
Hello. Thank you for that speech. And my question is, you said about some in-memory calculations. Are you about like HP machine or like that, something?
In-memory computing typically has this idea that you can use the analog properties of your RAM to do computation. The idea would be, for example, if I have neural network activations in RAM, I can read a whole line of activations that are supposed to be summed up, and I use analog computing to sum them up. Basically, just read the voltage when you connect all of these lines at the same time. That lets you, add up thousands of vectors, or 512 vectors of 512 elements. Really good if you can use it. Problem is typically in the interfacing with it. There's a lot of existing approaches, but shipping hardware and actually having it usable are two different things. But it is a very exciting area. So yeah, I hope that answered your question.
Okay. Yep.
Is one more? Yes.
Hi. Very interesting approach. So in the last slide, I just want to make sure that I got it right. Basically, I'm someone who used, for example, Cadence to silicon and try to exactly what you said. Like we had to think still in a hardware way and write software. It's not natural. So I just wanted to make sure that if I got your message well, and maybe to define for some people here. So basically, the idea is to find the part of software which is problematic in performance way, and then just as if it was written in C++, on Java, or something like that, and try to somehow translate it to hardware.
Yes.
But somehow is basically what your company is doing. Maybe that's something that's missing here and which is not really clear for me how that's done.
You can view it as an EDA company, as in you give me all of your software and I convert it into circuitry and you keep maybe writing your software to design actual hardware, or you can view it as a sort of a platform as a service. Think of it as a Lambda, AWS Lambda for hardware. Basically, give me a function, you don't need to care about how it's deployed. It'll just be a bit more efficient or faster and so on. It'll make you savings, or if you want to clock it really high, it'll give you better latency.
Okay, and this is for systems that already have, for example, FPGAs available?
Yes.
Okay.
But we are lucky that both AWS, Microsoft, and a bunch of smaller clouds do have FPGAs. They are reaching adoption. What was pretty helpful was for the two biggest CPU companies to just snatch them up and start fabbing.
Nice, cool approach. Thanks.
There was a question somewhere here. No?
No. Okay.
All right. Thank you.